This method, a quick history, that originally it was developed by C.A. Cornell, Alan Cornell, in late 1960s, and then this method or this idea was used by Professor Algermissen for developing the first ever PSHA maps for US, and then this methodology was also later used in developing the US seismic zone maps in the UBC series of building codes. So from 1988 onwards, 1991, then 1994, and finally in 1997, this PSHA methodology was used to develop the US seismic zone maps. The idea was that we perform the PSHA for PGA, considering PGA as our hazard parameter, and then make different zones which have the same or similar range of PGA. So nowadays this method is widely used. Several of the new approaches also are developed recently in this PSHA methodology, but we will be studying its very simpler version, right. So I will give you just an overview of the overall methodology. So details I will just skip, and I have separate video lectures in which I go into a little bit more detail. This is the US seismic hazard map, PGA map actually, which was developed using PSHA methodology, and it is for 10% probability of exceedance in 50 years, and you can see that it is 1976. Different zones are developed in it. You can see, for example, zone 5, similarly this one. So all of these contour lines have actually these are, I think, not zones, maybe these are the values of the PGA. So all these contours are actually showing the values of PGA corresponding to 10% probability of exceedance in 50 years. Similarly, this is another seismic zone map. So this is zone map, the previous one was actually the PGA map. So PGA ranges are used to convert it into zone map. So here you can see 0, 1, 2A, similarly you will also find 2B, 3 and 4 also. This is the seismic hazard map for Pakistan, which was developed as part of a recent study in NUST. So here also you can see that these are the PGA values. Nowadays, instead of using contour lines, we use colors. So different color ranges are showing the PGA values, and they are corresponding to 10% probability of exceedance in 50 years. So this is DBE level, you can say, PGA map. So and obviously this is the final output of that detailed PSHA process which was done before that whole result. This is for MC level, 2% probability of exceedance in 50 years. Obviously the numbers will be higher, and these are PGA values, and you can see that the pattern of hazard is somehow matching with the seismotectonic setting and also the historical seismicity, because actually the historical earthquake data, as I will show later, that it becomes the basis for future prediction or future forecast, right. So if you have more earthquakes at a certain location in past, when you apply that methodology, ultimately you will get a high hazard for that area, right, because the seismic sources which are in that high seismicity area, they will result in a high hazard for future also. So PSHA is an attempt to understand the actual level of seismic hazard. So in that attempt, there can be improvements which are continuous improvements. We have more and more sophisticated tools to compute hazard at a particular site, but ultimately whatever method we develop, the past data is the basis for that analysis. The data which is going to be processed and converted into future hazard, this color actually is actually the past data, right? So it is possible that we improve our analysis methodology, our computational power, and we also improve our historical data by digging out more data, and there are different ways that how we can improve our understanding of the past data. Then the new PSHA may result in a different hazard landscape compared to the previous PSHA, right? So for example, when I say that 2007 PSHA of Pakistan gave us one picture of hazard, and now 2021 PSHA gave us a slightly different picture, it doesn't mean that the hazard actually changed. Hazard is same, our understanding about that hazard is changed, right? So it may be possible that we used more detailed historical data for 2021. It may be possible because we considered the earthquake which occurred between 2005 and 2021. They are nowadays being recorded. It is very difficult to miss a major earthquake, right, which is not in our recordings. So as the data set which is the basis of this PSHA is improving, the hazard picture which we get at the end is also improving, but it doesn't mean that the hazard is changing, right? So it is possible that the new PSHA results in lower values compared to previous. It is possible that the new PSHA results in higher values, and obviously the zone which you asked is actually the result of that PSHA process. So ideally, yes, it is possible that the zone of a particular area is changed as a result of new PSHA. It may go up or down depending upon the new results, supposed to be more accurate, right? But in this new seismic design philosophy, you don't need those zones, PGA based zones. You directly need SS and S1, right? So actually this map doesn't have direct application nowadays, this PGA map in seismic design procedure. We must have an SS map or S1 map like this, and that also can be developed using PSHA. All you need to do is that use the GMP for SS and use the GMPs for S1, and everything will be same. Your hazard parameter is changed, right? So instead of making a PGA map, you can make an SS and S1 map, and that will be compatible with your seismic design philosophy which is currently being used, right? So once we do PSHA, and we have done it several times here in NUST for whole Pakistan using different techniques, using different assumptions, or check the adequacy of a particular assumption and then improving our input data, for example. So we perform it for all hazard parameters. Once you make a detailed seismic source model and run it, you can run it for SS, you can run it for S1, you can run it for any spectral acceleration. So we make maps for everything: PGA, SS, S1, spectral acceleration at 2 seconds, spectral acceleration at 3 seconds. You can it is your choice, that it's just a matter of running the analysis again and again. So this is an final output of PSHA process, actually one of the many outputs from PSHA process. This gives an overall picture of the hazard, but I can also pick one particular site, for example this one, and PSHA will also give me the spectrum of that at that particular site. The SS and S1 values or PGA values can be directly used to pick from this map. And then also different maps for different hazard levels. DBE level, different map. MCE level, different map. Similarly, service level, different map. Or any other level, intermediate level, different map, right? So PSHA also will give you hazard values at different definitions of hazard. 2% probability of exceedance, 10%, 5%, 20%. You can just run it again and get new values. This is the hazard assessment result of an international program to assess the seismic hazard of the whole world, called G-SHAPE, Global Seismic Hazard Program, Assessment Program, G-SHAPE, and it gives us in just one picture it gives us what are the you can say areas with high hazard or what are the areas with moderate to low hazard. So you can see here Pakistan was also part of that study. I will show you an enlarged view of that map also for Pakistan. But obviously this will be some PGA value, I think, or some other hazard parameter. So key assumptions in PSHA. First of all, we assume these are 5 basic assumptions in the original classical PSHA method. First assumption is that earthquakes occur within a defined seismic source zones or along the defined active faults, or I can also include at certain points. So the first concept which you should understand is this concept of seismic source zones, or actually seismic sources. There can be 3 kinds of or 3 types of seismic sources: area sources, which can be called as seismic source zones, then line sources, which are active faults, and there can be point sources also, right, at a particular point. So let's say that I want to perform PSHA of this area. I have to identify all the seismic sources which can produce future earthquake. And how I will do it? That I will look at the historical seismicity pattern, historical seismicity data. Let's say that I have the data of last 100 years for this my area, right. So I plot all 100 years earthquake data, and let's say it is all the epicenters are these dots. Then I will carry out a detailed study to identify the seismic sources, right, and I will come to know, let's say, that there is a fault line here which produce most of these earthquakes which occur in its vicinity. There is a point source at this location and at this location, and then still and that point source produce all those nearby earthquakes. This one also nearby earthquakes. This is the fault line. Still there will be some past earthquakes which will not be, which you cannot associate with any particular fault or at particular volcano, for example, right. Still there will be some earthquakes, you will not be able to find their cause, you will not be able to associate them with any particular fault, right, because they may look very far from a particular fault or some other reason. For those earthquakes, you will make area sources or source zones. So I will use the word area sources, which is more convenient. So I will make some area sources like this, and I will treat that whole area as a source, as something which produces earthquake in past and actually which can produce an earthquake in future also. So the whole area, let's say this is the shaded region, this whole region will be declared for the purpose of PSHA as a source, right. And this is more convenient concept because most of the earthquakes in several of the study regions, you may not be able to attribute them to a particular fault, right. What will happen if your study area is like this and your most of the historical earthquakes are almost equally distributed? How will you then you can say associate them with particular fault line? So what you will do in all such cases where you will unable to find the actual source in the form of a particular fault, you make area sources there, right. So in that case, I will say that this is my area source A, this is my area source B, and this is C and this is D. So in my whole study area, I have 4 sources, right. It's like having 4 faults, but obviously we will have area sources in this case. And in any other particular study area, we may have some fault or line sources, some area sources, and maybe some point sources also. So sources can be of 3 types, right. Line sources and point sources are clear, but area sources is a new concept for you, right. So when we have some past earthquakes in a particular area, but we cannot associate them with any known fault, right? There may be a fault there, but maybe it is not known yet, right? So in all those cases, what we do, we make it an area source, right? So we treat it as some source which is producing earthquake in past frequently, and which is also expected to produce in future also, right? Now once we make any source, whether it is area source or line source or point source in our study region, then we assume that earthquakes occur randomly at any location with an equal chance. Within one source, we cannot assume that at one location earthquake occur more and another location earthquake occur less. So within each defined seismic source zone or active fault, earthquakes occur randomly at any location with an equal chance, right? So that's why, if for example, let me go here, maybe somewhere, maybe here at the bottom, this is my study area, and historical seismicity for last 100 or 200 years looks like this. Let's say there is a very detailed cluster of past earthquakes, and then some other earthquakes which are not that closely, you can say, located. So what you will do, you will make this whole region which have almost the similar seismicity pattern in history, you make it as one source, let's say source A, and then this source you may consider it as B's. So it's the choice of the hazard analyst to delineate these seismic sources. This is one of the major challenges actually, because this may affect our future forecast results, hazard results, right? But once we make a source, for example, A source is delineated and we declare it as one area source, then within that source we cannot say that in this particular region earthquakes occur more and in this region earthquakes occur less. In that source, we assume that the activeness of that source is constant in that whole source which we just declared. Similarly is with faults. If there is a fault, let's say source C, which is a fault, along the length of that fault we cannot say that in this region earthquakes occur more and then in this region earthquakes occur less. Once we declare it as one source, then the earthquake can occur randomly in future at any location with equal chance, right? So if there is a fault which is continuous and at one location you have more historical seismicity and at the other location of the same fault you have less historical seismicity, then you divide that fault into two sources, right? Because once you declare that as one source, then you are basically assuming that in future the earthquakes can occur randomly at any location along the length of that fault with equal chance, right? So you divide that in case of two sources if it is distinctly behaving differently in two different regions of length, right? So this is our second assumption of PSHA, right? That we have to make zones, but then within each zone, the zones should be such that within each zone we should be able to assume this thing, that within one source the occurrence is random. It's not more at one location and less at the other location. It is random. Then third assumption is that within each defined seismic source zone or line source or area source, earthquakes randomly occur in time in which the average rate of occurrence is defined by its magnitude recurrence relation. I will introduce this relation. This is a relation which tells us that how active or less active a source is, right? If a source is producing earthquakes more frequently, it is more active, and if it is producing less frequently, it is less active. So the activity rate of any source is quantified by this relation, magnitude recurrence relationship, and as the name indicates, it is a graph between magnitude which that source can produce and recurrence, how frequently that magnitude is produced by that source. So it's a graph for each source which you will construct for each source, and that graph will tell us that how active or less active that source is. So, but the main assumption is that the earthquakes randomly occur in time. In historical data, there will be no pattern. This assumption that earthquakes occur randomly in time is sometimes called Poissonian's assumption. Any process which occur random in history, we can model that process as the Poissonian process or Poisson's process. So, earthquake phenomena or this process is Poisson's process. In other words, if an earthquake occur, for example, magnitude 6 occurs today, then the possibility of magnitude 6 occurring tomorrow is not less than that previous event. It will still same. This is what I mean by random occurrence in history, right. So, they are completely, they do not have any memory. If an earthquake occur today, it does not mean that tomorrow now we have less chance of any earthquake. This is what I mean when I say they occur random in history. This is Poissonian process, and this is one assumption which we make in PSHA, which means that we do not consider dependent earthquake events in PSHA forecast or prediction. Dependent event mean that now if I have a main shock today, now I know that there will be a dependent event which is aftershock tomorrow or any other day after that earthquake. So, aftershocks are dependent on main shock, right. So, we do not consider dependent events in future forecast. So, all the aftershocks and foreshocks should be removed from the historical data, and the data which should be used for future forecast should only contain main shocks, and main shocks are assumed to occur randomly in the history, right. They are independent events. We have a very narrow slice of data like 100 or 150 years, which is nothing compared to the scale at which this whole phenomena works. Energy may keep on accumulating for thousands of years and release one day, right. So, we may not have major information about the pattern or any other information about past earthquakes in that narrow slice, right. The next assumption is that the occurrence of earthquake is statistically independent of the occurrence of other earthquakes. As I have said, that they are statistically independent. One earthquake is not dependent on any other earthquake. This is an assumption made for PSHA. And then lastly, we can predict, this is an assumption that it is possible to predict the PGA value or any spectral acceleration value at your site using GMPs, which can just take earthquake magnitude, source to site distance as a primary input. There can be some other inputs like faulting mechanism, site class and others, but these are the two main inputs in GMPs. So, GMP is also one assumption in PSHA process, right. Obviously, these kind of equations are approximate. They are made from large data sets of past earthquakes, recorded earthquakes. So, they can be used for the prediction of future ground motions given a particular magnitude and source to site distance. So, GMP or attenuation relationship is also an assumption in PSHA process. So, using these assumptions, we perform that analysis. So, this is the objective, PSHA procedures objective. You have a source A, this is your site for example. You have a source A and this is an area source now. So, now you are familiar with a source which have a particular area. So, obviously there will be a cluster of earthquakes in past and the analyst declare that as source A. Source B is a fault line, source C is also a fault line, source D is also an area source, right. And your site is located at different distances from these four sources. your objective is to calculate the hazard parameter at your site. If it was DSHA, it was very simple. You consider each source separately and maximum magnitude which that source can produce and distance, apply GMP, predict any number you want, predict the whole spectrum, predict the spectral acceleration at any particular time period, predict PGA. DSHA doesn't allow you to have to know the probability of exceedance associated with the PGA number. So it may not be possible to get a number for different return periods, right, using DSHA. But PSHA allows you to have that PGA number, which is the function of the probability of exceedance or return period, right. So now the output of PSHA procedure at any particular site is not just one PGA number or one SS number or one S1 number. It is a whole curve between that hazard parameter on x-axis and the probability of exceedance on y-axis. This curve is called hazard curve. Hazard curve. So you have the probability of exceedance in certain years. In certain years of exposure on y-axis, and the peak ground acceleration or any hazard parameter on x-axis, and PSHA will allow you to construct this whole curve, right. This whole curve will be the output of PSHA and not one number. So now you can know that, for example, if I want 10% probability of exceedance in 50 years, if this is my definition of hazard, probabilistic definition of hazard, and these certain years is, let's say, 50 years, you will simply go for 10% number and pick the PGA value. This is your dBE level PGA. If you want to know the PGA for MCE level, 2%, so you simply go for 2% probability of exceedance and pick another PGA number. So contrary to DSHA, where you only get one number, and that is the most supposed to be the most conservative one, here you get that number as a function of probability of exceedance, which can also be converted into return period. So now you get a number which is a function of return period. So now it's your choice that you fix one particular you can say one particular definition of hazard you fix and pick the PGA for that particular site, right. So that's how we can make a separate hazard map for dBE level and a separate hazard map for MCE level. Why? Because in picking the hazard parameter at each pixel or at each site, we use one time we use 10% and next time we use 2%. So we get two different numbers for the same site. So using one number we make dBE level hazard map, for another number we make MCE level hazard map. This is not possible in DSHA, right. So this is the final output required. This hazard map, hazard curve can be converted into map if the curve for each point is available, right. Similarly, you can also use this hazard curve to construct the spectrum at your site for any dBE or MCE level. And that the process goes like this, that once you perform PSHA for this particular site using PGA as your hazard parameter, then you repeat it and use SS as your hazard parameter, then S1, then S1.5, then S2 second, 3 second. So you use spectral acceleration at different time periods at your hazard parameter. So you may get a family of hazard curves for the same site as a result of PSHA. So you get, for example, one curve for PGA, this is PGA, then you get another hazard curve for the same site for SA at 0.1 second, then another curve for SA at 0.2 second, then SA at 0.3 second, and so on. So you can change your hazard parameter every time for the same site, for the same everything, and construct a different hazard curve for the same site. Then what you can do is that select one definition of hazard, let us say 10% probability of exceedance in 50 years. So this is, let us say, this number on y axis, 10%, 10%, all curves you just pick the number for 10%, right. So this is the PGA for 10% probability of exceedance. This is the spectral acceleration at 0.1 second at 10% probability of exceedance. Similarly 0.2 second, 0.3 second. So you pick all these numbers and can finally construct the response spectrum of your site. Spectral acceleration versus time period. The starting point will be PGA, and then for any time period you know the spectral acceleration for one fixed definition of hazard. So if you use dBE level definition, 10% probability of exceedance, this is the curve for 10% PE in 50 years, or dBE level, right. So you can construct a dBE level curve from the PSHA for your site. Then you can also construct a MCE level curve, obviously that will be like this, above than this, or SLE level, which will be lower than even dBE level, or any intermediate level. So this is the beauty of PSHA, that it allows you to construct the hazard definition or response spectrum or any other parameter at any return period. So you have many choices then, and obviously if the structure is more important, it should be designed for a higher return period, and if it is less important, can be different. And for example, buildings are designed on a different return period, bridges are designed on a different return period, dams and other hydraulic structures can be designed on different return period. So now you have the whole picture of hazard, not only one number as given by DSHA. So one more thing is that since in constructing that one particular line, spectrum of the future earthquake, you considered one fixed definition of hazard in picking the number from all hazard curves for one site. This spectrum is called UHS, Uniform Hazard Spectrum. Uniform Hazard Spectrum. So the response spectrum by default is UHS, right. Why uniform hazard? Because there was a fixed definition of hazard assumed to construct that. So each point on one particular curve represents the same hazard, right. It is picked for the 10% probability of exceedance for all spectral accelerations, or picked for 2%, or picked for any other number. So that's why this type of spectrum is called UHS, right. So when we say simply response spectrum, we mean UHS, right. But there is a more sophisticated concept called CMS, conditional mean spectrum, which have a different theoretical background compared to UHS, right. So this is the objective. Now objective is clear, that you need to construct hazard curve for each site in the study area. Once you construct hazard curve for each site, all other quantities are derived from that, right, derived from that. If you want to make PGA map for dBE level, pick the PGA values corresponding to 10% probability of exceedance for each site and make a map. So ultimately the main primary output of PSHA is the hazard curve for each site. If you want to perform site specific PSHA, then you just need to do it for one particular site. It is site specific. But if you want to make a map, then do it for all sites, right. Repeat that process for each pixel in the study area so that you can make a map, and you can also do it for one particular site.